Plate load test. Plate load test is a simple test that is used to calculate bearing capacity and settlement in field. So it has a plate and a hydraulic jack to apply load. Again, very simple test. We have a plate, place it on top of the soil layer. A hydraulic jack is used to apply load to measure the actual bearing capacity and settlement. So again, we have a plate and load is applied. We measure load per unit area, or Q, load per area, and we measure settlement. And then we have our load per unit area versus settlement curve. So when we have the results from plate load test, we can use that to calculate ultimate soil bearing capacity of the actual footing. So we use a plate, apply load, we measure load per unit area or capacity of plate, and we measure settlement of plate. Then we use these formulas to calculate bearing capacity of footing and settlement in footing. You need to pay attention to the type of soil. In clay soil, ultimate bearing capacity of footing is equal to ultimate bearing capacity of plate. So whatever we get from the test, that's actually the ultimate bearing capacity of footing. But in sandy soil, ultimate bearing capacity of footing is equal to ultimate bearing capacity of plate, which we get this from plate load test, times width of footing divided by width of plate. This is width of plate. We also know what is width of footing. We can calculate ultimate bearing capacity of footing when we do the plate load test and have the result for ultimate bearing capacity of plate. Same thing for the settlement calculation. Again, we have a plate with a certain width, apply load, and calculate bearing capacity of plate as load per area of plate. Also, we measure settlement of plate. Now we have the formulas to find settlement of footing when we have settlement of plate. So in clay, settlement of footing is equal to settlement of plate times width of footing divided by width of plate. If we have sandy soil, this is the formula that you need to use. Settlement of footing is equal to settlement of plate times 2 times width of footing divided by width of footing plus width of plate. All of these to the power of 2. And that's how you calculate ultimate bearing capacity or settlement in a footing using the results from plate load test. For example, the ultimate bearing capacity of a 700 millimeter diameter plate. So we have a plate, diameter is 700 millimeters. Then we apply load and QU of plate is equal to 280 kilonewtons per square meter. This is the result from plate load test. The question is asking us, estimate the ultimate bearing capacity of a circular footing with a diameter of, so now we have a footing, diameter is 1.5 meters. The type of soil is sandy. So it's asking about QU of footing when we have QU of plate. So you need to go to the slide where we have the ultimate soil bearing capacity and select the formula for sandy soil. That's the formula we need to use. So this is the formula. You have your formula here, and then you just plug in numbers into the formula. QU of footing is equal to QU of plate, which is 280 kilonewtons per square meter. Width of footing, which is 1.5 meters, when divided by width of plate. So width of plate was in millimeters. We need to convert millimeters to meters. And this is QU of footing. This is really important that you pay attention to the type of soil and select the correct formula to calculate bearing capacity of footing when we have bearing capacity of a plate for the plate load test. Okay, let's go over more examples. So this is what we talked earlier based on Terzaghis bearing capacity failure for shallow foundation. We can calculate the ultimate bearing capacity from a strength coming from cohesion, coming from surcharge, and coming from unit weight of soil. We said that this is width of foundation and this is depth of foundation, and then we have these three formulas. You need to select the correct formula based on the shape of foundation. You can use these formulas when there is no groundwater table in the vicinity of your shallow foundation. If we have groundwater table and it's above the bottom of footing, then you need to make adjustments to your formulas. So instead of here, we have a moist unit weight and below groundwater table we have saturated unit weight. So instead of gamma, we need to use effective gamma, which is gamma saturated minus gamma W. Gamma W is 62.4 pound per cubic feet. Also, instead of Q being gamma dF, now we have Q as gamma H plus gamma prime D. This distance is H from the top of the soil to the top of the groundwater table, and from groundwater table to the bottom of footing is D. Also, another important formula, if we want to do the settlement check and limit the settlement in a structure, this is the formula to find the minimum required width of footing to limit settlement. Okay, so these are the most important formulas for shallow foundation design. We have a square foundation. So this is a square foundation, 6 feet by 6 feet. The soil supporting the foundation has a friction angle of 25 degrees, cohesion or shear strength of 350 pounds per cubic feet. Moist unit weight of soil is 120 pounds per cubic feet. The question is asking you to find allowable bearing capacity, which is equal to ultimate bearing capacity divided by a factor of safety. And the factor of safety that we need to use is 4. We have depth of foundation as 4 feet and width of our footing 6 feet. So the first thing that we need to do for shallow foundation, this is an example of a shallow foundation, and we want to find ultimate bearing capacity, which is coming from the strength as a result of cohesion, surcharge, and weight of soil. So you need to use QU formula for a square foundation. Again, because we have a square foundation, this is the formula that we need to use. Friction angle, internal friction angle is 25. So these are our N, C, N, Q, and N gamma. There's no groundwater table, so we can use this formula to calculate surcharge. Depth of foundation, width of foundation, moist unit weight, and factor of safety also provided for us. So we just need to plug in the numbers into the formula. We have 1.3. This is the formula for a square foundation. And it's a shallow foundation. Cohesion 350. NC we have from the table. Q we said it's gamma DF. Gamma 120 pounds per cubic feet. DF is 4 feet and NQ is 12.72. 0.4 times gamma, which is 120. Width of foundation and N gamma. So this is our ultimate bearing capacity for our shallow foundation. But the question was asking for allowable, and allowable is when we divide ultimate by a factor of safety. And this is our allowable bearing capacity. Next question. So again, we have a square footing, that's shape of footing that is important for us. And the question is asking us to find the gross allowable load. So pay attention that now we have uppercase Q. Load is different from bearing capacity. So this question is asking for allowable load. And we also have groundwater table above the bottom of footing. So here we have moist unit weight as 110 pound per cubic feet and saturated unit weight below the groundwater table as 120 pound per cubic feet. Cohesion is 0, there is no clay. Friction angle 30 degrees. Width of footing 6 feet. Total depth of footing 5 feet. H, which is from the top of soil to the groundwater table, 3 feet. And D, from groundwater table to the bottom of footing, is 2 feet. So we need to calculate allowable bearing capacity, which is ultimate bearing capacity divided by factor of safety. And then allowable load is allowable capacity times area. So we need to start by calculating ultimate bearing capacity for a square footing. We do that, then divide that number by factor of safety. We get allowable bearing capacity. Then multiply that by the area of footing and we have load. So we have a square foundation. This is the formula that we need to use. Friction angle is 30 degrees. So these are our N, C, N, Q, and N gamma from the table. Total depth of foundation. Depth of foundation is H plus D. Total depth of foundation is 5 feet. H is 3 and D is 2 feet. Width of foundation is 6 feet. We have moist unit weight. This is moist unit weight. And we have saturated unit weight. So effective unit weight is saturated minus gamma W. And when we have groundwater table above the bottom of footing, instead of using gamma DF, we need to use gamma times H plus gamma prime times D. C is 0, which makes the first term in our formula equal to 0. Then again, then the Q for case 1 is gamma H plus gamma prime D. So we have gamma times H plus gamma prime, which is gamma saturated minus gamma W times D. So this plus all of this. And then you multiply this by NQ. The third term, we have 0.4 times gamma prime. Gamma prime again is gamma saturated minus gamma W times B times N gamma. So if you do the calculation, you get the ultimate bearing capacity. The question is asking for QA. So we need to calculate allowable bearing capacity. Allowable bearing capacity. This is allowable bearing capacity, or QA, is equal to ultimate bearing capacity divided by factor of safety. And then allowable load QA is capacity times area of footing. We had a square footing, 6 feet by 6 feet. So area is 6 to the power of 2, or 36 cubic feet. So this is area of footing. This is allowable bearing capacity. It will give us allowable load. Example number 7. We have a square footing. Width of footing is unknown. The square footing rests on a uniform, thick deposit of a stiff clay. So it has high cohesion. Shear strength or cohesion is 1,000 pounds per square feet. The question is asking us to find the required dimension of a square footing in terms of bearing capacity. So just the bearing capacity check. So that the footing can carry a proposed total load of 200,000 pounds using a factor of safety of 3. There is no groundwater table. Moist unit weight is 120 pounds per cubic feet. Friction angle 0 degrees, and depth of foundation is 5 feet. So we need to find ultimate bearing capacity. We have Q applied, and then we can find the minimum required width to avoid failure. The first thing that we need to do is again to find the ultimate bearing capacity of this square footing. So we have a square footing. This is the formula that we need to use. Cohesion is 1,000 pounds. Friction angle is 0. So we have these NC, NQ, and N gamma. These are from the table. Depth of foundation is 5 feet. Width is unknown. That's what we want to calculate. Moist unit weight is 120 pounds per cubic feet, and factor of safety is 3. So we start from here, plug in the numbers, and we are doing only the bearing capacity check. 1.3 times C times NC. There is no groundwater table, so Q is gamma times dF, surcharge. We have gamma times dF times N gamma, and NQ is 0. Sorry, here is NQ. N gamma is 0, So the third term is 0. This is the ultimate bearing capacity. We need to calculate allowable bearing capacity. And allowable bearing capacity is ultimate bearing capacity divided by factor of safety. So this is our allowable bearing capacity. This means that we can cause a stress. This footing can carry a stress up to 2,670 pounds. So this is how much we are allowed to apply, which means that the load applied divided by area of footing should be equal or less than this number. So 2670 pounds per cubic feet. Load applied, this is how much load is applied from superstructure, is 200,000 pounds. Area of footing is unknown, but we have a square footing with a minimum width of b. So area is b squared. If you rearrange this formula, you get that b squared should be higher than 200,000 pounds divided by 2670 pounds per square foot. And you get the required minimum width. That's the required minimum width of footing to avoid bearing capacity failure when 200,000 pounds is applied to this footing. Okay, the next example is from plate with a width of b and load. So we have plate load test. A plate load test was conducted in a clay soil in which the size of the bearing plate, so width of plate is 0.5 feet, and the ultimate load per unit area for the test, the ultimate load per unit area for plate is 1550 pounds per cubic feet. Estimate the total ultimate load, again this is load, for a real footing size of 5 feet. So now we have width of footing as 5 feet. If you go back to the beginning of this video, we went over the formulas which you can use to calculate bearing capacity of footing when we have the plate load test. So for clay soil, the ultimate bearing capacity of footing is actually equal to the ultimate bearing capacity of plate. That's only for clay. So the ultimate bearing capacity of footing is 1550 pounds per cubic feet, but the question was asking for load, and remember load is bearing capacity divided by area of footing. So the answer to this question is when you multiply 1550 by area of footing, and footing that we have is a square footing with a width of 5 feet. So this is area of a footing with a width of 5 feet. Question number 9. We have the results from plate load test. This is in sandy soil. So this is really important. We have sandy soil this time. The size of the plate is, so width of plate is 0.4 meters. And we have a square column foundation, so width of footing is 5 meters. The column needs to carry a load of 2500 kilonewton. So load that we have is 2500 kilonewton. What would be the estimated settlement of the actual footing? Here we have load per unit area, and here we have load. So the first thing that you need to do is divide load by area of footing, which is 2500 kilonewton divided by footing is 25 square meter. This is 100 kilonewton per square meter. Then we come to the plate load test results. We find 100 kilonewton per square meter. Go to the curve and find the settlement. This is 3 millimeters. So if the load per unit area is 100 kilonewton per square meter, it will cause 3 millimeters settlement in plate. That's plate's settlement. We are looking at this, we want to find the settlement in the actual footing, and it's in sandy soil. So again, you need to go back to the beginning of this video and find the settlement formula in sandy soil. So in plate, we have 3 millimeters. Width of footing is 5 meters. Here is 5 meters, and this one is 0.4 meters. Just plug in the numbers in the formula, and you will get settlement in footing is actually 10 millimeters.